doing Chapter 8, Section 2, Area Surface of the Revolution. Now, if you recall, the surface area of a cylinder is 2 pi r, which is your radius, times the length. Well, if you take a look at our surface area of revolution formula, it's actually there's a lot of resemblance between those two formulas. So for example, we have the actual formula for this. It's going to be the integral from a to b, 2 pi f of x, which is basically your r, times square root of 1 plus f of x squared dx. So if you notice, the 2 pi r is basically, the radius of the cylinder is basically the f of x for this formula, and the length, if you recall from the previous section, is basically your arc length. So that being said, this formula is used when it is asked to revolve around the x-axis. And there's actually an alternative formula for this that you get to use when you have a certain circumstance, which I will further speak about when we do an example. So the alternate formula is surface area equals the integral from a to b 2 pi y ds, which your ds is basically your arc length. But look at this, it's times y, not f of x. And this you get to use when, for example, they tell you to revolve around the x-axis, but your equation is in terms of x, and your equation is in terms of y, and your intervals are in terms of y. So when they're opposite that way, you get to use this one. The same thing goes when it's in terms of y, when it's revolving around the y-axis. So the formula is the integral from a to b 2 pi f of y times the arc length, so 1 plus f prime of x squared dy. So the same thing goes to this one. The alternative formula is s equals the integral from a to b 2 pi times x dx. So as you can see, they will be asking you to revolve it around the y-axis, and if the function is in terms the opposite, which would be x, if it's in terms of x and in terms of the intervals are in terms of x as well, then you get to use this one. So now that we have down the 4 different formulas, technically it's one, but I like to think of it as 4 different formulas. Let's get down to examples. So we're going to do one of each so that you can see which one to use and when to use it. So our first example is going to be this one. We use that one. So it's y equals 1 plus 4x with our intervals from 1 to 5, and it's going to be around the x-axis. Okay? So as you can see, it is in terms of x, our intervals in terms of x. So it works out well, so we get to use the original formula. So it's going to be from a to b 2 pi f of x 1 plus. And I like to rewrite it always, the formula, because it's the more you write it, the more you say it, and the more practice you get. So it'll be better for you to actually, learn it. So now that we have that, what I like to do first when it comes to this is first calculate the arc length. So I first, do the derivative. So dx over dy, which equals, if we put it into exponential form, it would be easier to take the derivative, so it would be 1/2 1 plus 4x to the negative 1/2 power times 4 for the derivative of the inside. So we would end up getting 2 times 1 over 4x to the negative 1/2. So now that we have that down, we get to put it inside our arc length form. So we put 1 plus 2, 1 plus 4x to the negative 1/2. That's squared. We end up having 1 plus 4 over 1 plus 4x. So we want to use common denominators. So we have 4x plus 5 over 1 plus 4x and the interval of that. So now that we have this, we get to use our formula. So when we put it back in here, it's going to be from 1 to 5, 2 pi f of x, so we get to put our function, 1 plus 4x, our arc length, which is 4x plus 5. And we actually want to divide this, and you'll see why. When we divide this, 1 plus 4x, these cancel out. So now, you get the 2 pi out, integral from 1 to 5. So then, we actually turn this into exponential form. So 4x plus 5 to the 1/2 dx. Oops, forgot the dx here too. Okay, so when we have this down, we actually can't solve this just easily like that. So then we let u equal, we use u substitution, which is, we let u equal 4x plus 5. So u equals that, which that is easy to take derivative of, which is just 4 dx. Okay, so having that down, now we plug it back in. So we have 2 pi over 4 because of this 4. The integral from 1 to 5, u to the 1/2 du, which when we integrate this simplifies to pi over 2, and that would be 2 over 3 u to the power of 3 over 2, and the interval from 1 to 5. So, and now what I like to do is I like to plug in back my u. You can also do is plug in your intervals into here, and that way you don't have to put it back. But I like to do it that way. I always like to put back my u's. So when I put it back, I would get pi over 2, actually pi over 3, sorry for that, pi over 3 because these would cancel out. So you would get pi over 3, 4x plus 5 to the power of 3 over 2, and the intervals from 1 to 5. So when we have that, when we plug in our intervals, we end up having pi over 3 25 to the power of 3 over 2 minus 9 to the power of 3 over 2. And our final, this would be pi over 3, and this would actually be basically 25. This, when we subtract from this, would end up being 98. So our final answer is 98 times pi over 3. Okay? So, as you can see, the functions are in terms of what they want you to revolve it with, in terms of x, around and around the x-axis. So you get to use the original formula in terms of x. Okay, so now let's use the alternative formula. Okay, our alternative formula. So, second example. X equals 1 plus 2y squared. Our intervals from 1 to 2, and it's going to be around the x-axis. Okay? So for this, as you can see, our function is in terms of y. And our intervals are in terms of y, but they want us to revolve it around the x-axis. So what originally you would do, I guess, we do is actually put this into terms of x. But instead of doing that extra step, you would skip that and you would just use the alternative formula, which is the integral from a to b 2 pi y ds. So having that said, let's start solving for our arc length. So our derivative would be 4y, and when we put it into our arc length form, it's going to be 1 plus 4y squared, which we end up getting 1 plus 16y squared. So now that we have that, we get to put it back into our formula. So it's going to be 1 integral from 1 to 2 pi y. So as you can see, we don't plug in the function. We leave it as y. Right here, we would plug in the function because it was f of x. But here, we just leave it y. Why? Because it's in terms of y. So we just put back in our arc length. So it's 1 plus 16y squared. So dy. So now we can't actually solve that, so we would use substitution again. So u equals 1 plus 16y squared. Du equals 32y dy. So having that said, we get pi over 2, pi times 2 over 32, the integral from 1 to 2. And as you can see, it works out well, so we just end up getting our substitution into exponential form du. So when we plug back in our u, it's going to be pi over 16 1 plus 16y squared to the power of 3 over 2. And this is an interval from 1 to 2. Okay? So, having that, we can now just plug in our intervals. So when we plug in our intervals, we get pi over 16, 65 to the power of 3 over 2 minus 7 17 to the power of 3 over 2, which our final answer would be 65 to the square root of 65 minus 17 to the square root of 17. And that's our answer. So as you can see, we just go heads on to resolving it instead of doing that extra step of having it in terms of x. Now let's go into in terms having it revolve it around the y-axis. So example number 3. Our equated function is x equals y to the third. The intervals from 1 to 2. And this is around the y-axis. Okay, so as you can see, how I like to say it, they pair up. This is in terms of y, and they want us to revolve it around the y-axis. So we get to use our original. So it's going to be the integral from a to b, 2 pi f of y, arc length 1 plus f prime of y dy. Okay, so now that we have that figured out, let's start our arc length. So our derivative is dy over dx, which is 3y squared. When we put it back into our arc length form, it's 1 plus 3y squared squared. So we end up getting 1 plus 9y to the 4th power. So having our arc length, now we get to plug it into here. So we have integral from 1 to 2, 2 pi, and then we plug in our function y cubed times our arc length, 1 plus 9y to the 4th power dy. So as you can see again, we're gonna have to use u substitution. So we have to let u equal 1 plus 9 to the 4th power so that we can end up getting this one, and it can all be easier for us to integrate. So u equals 1 plus 9 to the 4th power. So du equals 36 pi cubed dx. So since that works out perfectly well, we take out our 2 pi, which would be over 36, integral from 1 to 2, and that would be just u to the half power du. And now we get to plug in our what was u. So this would be pi over 18, 1 over, since we're actually integrating already, it's going to be 2 over 3 u to the power of 3 over 2, integral from having our intervals from 1 to 2. Okay? Oh, and actually, this is me. Alright. So, when we plug in back our u, we get pi over 18. We get 2 over 3, 1 plus 9 to the 4th to the power of 3 over 2, and then we'll from 1 to 2. And now when we actually plug in our intervals, this actually we can simplify this, which would be pi over 27. And we end up getting, when we plug in our intervals, we end up getting 145 square root of, so 145 to the power of 3 over 2 minus 10 to the power of 3 over 2. So our final answer would be pi over 27 times 145 times the square root of 145 minus 10 to the square root of 10. And that would be our final answer. And if, excuse my error, I forgot to actually let you know that from here to here, I actually integrated. So I actually skipped a step. So I integrated this, which would be 2 over 3 u to the power of 3 over 2, and then I just basically plug this in here. Okay? Just to clarify that. Alright. So having that said, let's do our last example. So example number 4. So we have 1 over 4 x squared minus 1 half ln of x. We're going to go from 1 to 2, and it's going to be around the y-axis. Okay? So if you take a look, it's having it revolve around the y-axis, but our functions, the function is in terms of x, and our interval is in terms of s. So they're opposite of each other, and because they're opposite of each other, we're going to do our alternative formula, which is integral from a to b 2 pi x ds. So having that said, let's solve our point. So when we do the derivative, it's dx over dy. Our derivative would be x over 2. It would be 2 over 4, which is 1 half times x. So x over 2 minus 1 half, because it's the consonant, and we just copy it down, and the derivative of ln of x is 1 over x, so it would be 1 over 2x. And when we put that into our arc length form, it would be 1 plus this whole thing squared. So we actually want to solve that. When we solve that, it would be x squared over 4 minus 1 half plus 1 over 4x squared. So we have combined like terms. When we combine like terms, we get x squared over 4 plus 1 half plus 4x squared. And this we can actually factor into this. But instead of having plus, instead of having minus, we get plus. So it would be x over 2 minus 2 over x squared. And since this is squared and they want us to take the square root, it's basically just down to x over 2 minus 1 over 2x. So now, having that, we get to put it into our formula. So integral from 1 to 2 pi x. Like I mentioned before, we don't put our function, we put just the variable x, and our arc length, which is not that, we solved that already. X over 2 minus 1 over 2x dx. Okay, so we take out the 2 pi. So it would be 2 pi, integral from 1 to 2. We distribute the x, so it would be x squared over 2 minus 1 over 2 dx. So this, as you can see, is very simple to actually integrate. We would have 2 pi. When we integrate this, it would be 1/2, it would stay there, and it would be x cubed over 3 minus 1/2 x, interval from 1 to 2. So we would have 2 pi x cubed over 6 minus 1/2 x times x, interval from 1 to 2. Okay, and when we plug in our intervals and then do common denominator, we would end up with 16 over 12 minus 12 over 12 minus 2 over 12 plus 6 over 12. Okay, so this would equal 2 pi times 4 over 12. So when we actually simplify this, our final answer would be 2 pi over 3. And that would be our final answer. So it does get difficult, it does get confusing when to use each formula. But my advice is that you first look at the function. Is in terms of the opposite? So if they're asking it to revolve around the x-axis, is the function in terms of x or is it in terms of y? And if you know that it's in terms of x, then you use what I like to call the original formula. If it's the opposite, if in terms of y, if the functions are in terms of y, then you use the alternative formula. And the same thing with the y-axis. So I hope this was helpful. It's actually my favorite section. So thank you, and I really do hope it was helpful.